Hi, I'm Caitlin Bate, Field Operations and Data Acquisition Coordinator at the Ocean Tracking Network. In this course, I'll teach you some basic functions in R. You'll learn about datasets, subsetting, and how to work with missing data. We'll explore tabular data and how to compare functions from the Tidyverse library with base R functionality, and then we'll begin experimenting with plotting. By the end of this session, you'll have the tools you need to get started with programming in R. This course is part of an acoustic telemetry workshop series with examples that will help you along the way. Before you get started, make sure to download and install the files required for this lesson using the link in the description so that you can follow along.
So hopefully you guys have already installed the Tidyverse package, and we're going to get down a little bit further to explaining what exactly that is. So I'm going to start by just running this library Tidyverse. So you can just click on it and do Control-Enter, or you can click on it and click Run up at the top here. So I'm going to highlight it so that you can see what I've selected, and I'm going to press Control-Enter. And it's going to tell me at the bottom in my console that it's working. So for people who aren't really familiar with R, this top left window here is your R script, your code, and this is a file that you can save and reuse, and you can comment with these little hashtags, and you can make headers, and you can see make headers with these dashed lines. If you want to see your section headers, you can click this button in the top right of your R script here, and it's basically like a table of contents. So I find that really helpful for making a nice clean R script file that you can then share like I have. Hopefully you guys also have this file open. So when I did library Tidyverse, it gave me a bunch of output in this bottom left screen, which is your console, which is where the code is actually running. So library Tidyverse was run, and then it's giving me some feedback about the packages that live within Tidyverse. So Tidyverse is, I think it's a library of several packages is the correct term. And then it tells me some conflicts. So this is saying that dplyr, the package dplyr, has a function called filter, and stats has a function called filter as well. So dplyr, now that we've just opened it, is masking the filter function from stats. Same with dplyr's masking lag. So those are interesting things to look at whenever you're librarying a package, is to see kind of what conflicts or masks might happen. In your top right is your environment. So this is where all your data objects and data files that you build in R will sit. So it shows you what's open in your R session. And then the bottom right is kind of a catch-all. So you have a file navigator. You have a plots window where your plots will show up as you make them. Some of us have already found that there's a packages list where you can see all the packages in your user library and update, delete, etc. There's a help tab, and then viewer. I'm not sure what viewer does, but generally I keep it on plots so that I can see what pops up, but you can explore. So I've libraried Tidyverse, which is the package that I want to start using in a little bit. And then the next step that's really important is we're going to set our working directory. So you have to tell R where on your computer you're working. So this is the path for me to the folder that has my R code and data file in it. However, for you, this will be named something different. So when you downloaded that zip file from the GitHub page and unzipped it and opened this R code, whatever folder that is in, you want to put the path to that folder in here. So set working directory will tell R where to look. So this is my path. The function for that is setwd. I'm going to select it, do Control-Enter. And how do you tell if it worked? I'm going to run getwd, and it's going to tell me what my working directory is. So get working directory. And you can see in my console now, it's printed it out, and that is correct. There's also another way to set your working directory, which is through this file navigator. You can navigate into it. There's like 3 dots here that you can click. and it'll open your Finder or File Explorer as you know it, and you can navigate in. And once you're in the folder you want, you can click More and click Set as Working Directory. So just some basic, like I'm going from scratch with R here. R has lots of different operators, so things that you're familiar with, such as addition, subtraction, multiplication, division. R also has some custom operators that are specific to the R language that we're going to go through, but in most basic terms, R is a computer, or a calculator as well. So if I just want to see 3 plus 5, I run that, and you can see in my console, it tells me that's 8, right? So basic math operators still apply. There's also another operator called the assignment operator. So this is how you build objects, variables, etc., and put them in your R environment. So this line of code is saying the number 55, assign it to a name or an object called weight kg. So if I run all of that, you can see now that there is a value in my environment called weight kg, and it contains number 55. The shortcut for the assignment operator is Alt minus. So you don't have to type it every time. I just find that helpful. You can also combine operators. So here we're going to do 2.2 times the weight kg object. So I'm just going to run that part. You can see it's 121. And then we're going to take all of that and assign the output to a new object. So now we can see we have an object called weight pounds, and it's 121. So this is just kind of really basic, showing how you can combine operators. Moving on, there's also functions, which are basically operations that are under the hood, so you don't have to type all the maths out, and they're contained in a function name such as square root. We're all familiar with the square root calculation. So instead of actually typing it out, there's a function called square root. So you can pass an argument to a function, so you have to tell the function square root what to work on. So we're going to square root weight kg and assign it to an object called 10, which is deceiving because it doesn't actually contain the number 10. But yeah. So you also can use functions without assigning them to anything. So here's round. I'm going to round pi, and it's rounded it. You can see the output. Instead of assigning to an object, the output shows up in my console, and it says 3. How do we know what arguments a function takes? You can run the function args against the name of the function you want to run. So round, we want to know what arguments round takes. So if we run args round, it's going to print out the arguments that it expects. So it says args round. It's a function. It wants an x, and then you can specify the digits. So anything that doesn't have an equal sign in front of it, for example, x doesn't say data equals x or something, that means it's mandatory. If it has a something equals something, that's already a default value, so you don't have to add it. However, if you don't like that default value, for example, I don't like digits equals 0, I want my digits to be something else when it rounds, you can pass that argument as well. Another way you can find that out is if you type question mark before the function and run that, it opens in your help viewer. You can expand it with this button. So rounding of numbers, it tells you what it does basically. It tells you the argument. So it wants a numeric vector for the argument x. And then for digits, it tells you that it wants an integer for the number of decimal places, etc. So that can be helpful. There's often example code and stuff in here for more complex functions. So we want to do it again, but this time we're going to pass a new argument to it. So the second argument, as we saw, was the digits. So we have x and we have digits now. So I'm going to run that. And now you can see that it's rounded to 2 digits. So this is just like super basic syntax in R, but if you have the arguments in the exact order that it's specified in like the help functions and in the documentation, you don't have to define which is which. So for this example, you don't have to define digits equals 2. You can just put 2 as the second argument because it's the same order, so R can understand what it's supposed to be. So run that, it does the same thing. However, if you're going to switch around the arguments, like let's say you don't remember which order they go in and you're just going to wing it, which is totally fine, make sure you specify which is which. So I can still do digits 2, x is pi, but because it's in a different order, you have to make sure you're specifying them. So that's just kind of some basic help when using functions. I know that round is a quite simple example, but hopefully you can see the value of how this could be expanded to some more complex functions and understanding how to use them. So we've so far just made some objects that only have one value in them. However, you can also make what's called a vector, which is a data type that has multiple, it's like a one-dimensional data type, similar to, I think, a list is what it's called in other languages. And to do that, we're going to use this function C, which means combine. So we're going to combine these values together, and we're going to assign them to weight grams. So run that. I can see weight grams is numeric. It has 5 values, and here's what they are. So you can see that appears. We kind of want to see a little bit about this vector we've created. You can run functions like length. It'll tell you how many values, what's the length of your vector. Class is a really great one. So we can see that our class of this vector is numeric. In this case, so numeric is, as you understand it, just some numbers. You can also do structure of weight grams. So here, you can see it's numeric, there's 5 values, and then it prints them out for you. So structure is a really great function to explore your data set. We're going to use it further down with some more complex objects. So we can see this is numeric. There's other classes, sorry. So there's character, which would be if it's words. Logical type is true or false. There's integers, which I believe is just like numeric, but with decimal places. So we're going to make a new vector, and this one's going to be a character vector, just to show you the syntax of what to do if you want to add words instead of numbers. So by putting the quotes around it, you can tell that it's identified as a character vector. It's a different color, and when you look in your environment, you can see the type is character. Or I'm going to type structure of my animals vector, and you can see that it's a character, and this is what it contains. So this is just some coding syntax, some R syntax. Anything in quotations is treated as a vector. So something that's really important is a vector can only have one data type in it. So if you tried to put some numbers and some characters in the same vector together, it's going to force them all to be the same type. So obviously you can't force like a word to be numeric, but you can force a number to be a character. So if I tried to add 17 to my animals and I run that, and then I tried to print it out, you can see that it has quotes around 17. It has forced 17 to be a character. So that's really important, because now I can't do math using that number 17 because it's treated as a character. It's treated as an object. It's treated like the word 17, like the word 17. It's not treated like a number with value anymore. So that's why it's really important to always check the structure of your vectors. And this is relevant because data frames that as you understand them, like, data tables, Excel sheets, kind of matrices, these are basically a bunch of vectors stuck together. So each column is treated as a vector in a data frame. So each column must have only one data type in it, and it will be forced to be all one data type. So when you're setting up your study or setting up your field sheets or etc., keep that in mind that you can only have one data type per column. So if you want it to be numbers, you can't have units in there as well. So you can't have like 3 feet in the same column. You'd have to have one column for the value and one column for the units because they're not the same data type. So just something that scaling up gets really important to keep in mind. So now we're going to learn some kind of basic subsetting in base R. So we haven't used any of the fun packages that I installed with Tidyverse yet. This is just all stuff that comes through basic R. So if you just call on your object, you can print it out in your console here. So there's our object. However, maybe I just want to see what the second value is. So there's the syntax with square brackets called indexing. So let me see the second value. So the second value, I already know it's rat, and you can see that when I do square brackets 2, it prints out rat for me. If you are familiar with other programming languages, a lot of them start indexing at 0. So my animals vector, mouse would be 0, rat would be 1, dog would be 2, etc. But R thinks like a human a little bit more, and it numbers them starting at 1. So mouse is 1, rat is 2, etc. So that's just something to keep in mind if you're coming from other programming languages. You can also index using some of the other operators that you might be familiar with. So for this one, weight greater than 50, or weight grams greater than 50, if you run that, it basically gives you results of these ones are false, these ones are true for each position in your vector of whether they are greater than 50 or not. And so we can use that as some indexing. So I've made a more complex example here to just showcase more operators. But so we're taking weight grams and we're selecting, so indexing is just subsetting. So we're subsetting where weight grams is less than or equal to 30, or, this is the or operator, where weight grams is equal to 55. So you have to use the double equal sign because that is looking for like a question, like where this is equal to 55. You're not saying that weight grams equals 55. You're not like assigning 55 to weight grams, etc. It's kind of like a test, so it needs a double equal sign. So anyway, if we run that whole line, you can see that it has indexed, it has selected where weight grams is less than 30 or it's equal to 55. So it's selected 2 values. Similarly, just to introduce other operators that we can use, we're going to select where it's greater than or equal to 30 and equals 21, which is impossible. So this particular example will give 0 results because there are no values that are greater than or equal to 30 and equal 21, because you can't be equal to 21 and greater than 30 at the same time. So that's just some introduction to subsetting and conditional indexing that you can use to subset your data or select values you're looking for. So the next section we're going to look at is missing data. We're going to make a new vector, and it's going to be called heights. And it's going to combine, so the C function again, it's going to combine all these values, including an NA. So we've built it. You can see it shows up here, and it's numeric. So we're going to maybe try to run a function on it. Let's try to find the mean of all our heights. Mean. Uh-oh. You can see that when we ran mean, it printed out NA. So it didn't calculate the mean. So some functions can't handle NAs. Some functions can't work when your data set has NAs in it. So there are ways to get around this. For example, you can use the option or the argument NA RM equals true. So NA remove NAs equals true. So I'm going to remove the NAs and then pass it to mean. And you can see now mean actually works. So other ways to get a data set without NAs, this will index, so we're using the square brackets, it's going to subset where it is NA for heights, except for when you have this exclamation point, it makes the function inverse. So this means is not NA now because we have the exclamation point operator in front of it. So we're going to now select where is not NA for heights. So you can see it's printed out everything except the NAs. You can also do NA omit and pass that to a function. So it's telling you that the NA action occurred at index 4, because that's where our NA was. You can also use complete.cases on heights and select just the complete cases. So there's just some other options for dealing with NAs, because an NA is different than 0. 0 is a real data point. 0 means something. NA does not. NA means there's nothing there. All right, so we've done a lot of experimentation with some one-dimensional stuff. We are going to move on to exploring data frames. So first, we're going to load ctrout.rda. So if your working directory is set correctly, it should find this ctrout object. All right, so I can see that in data, ctrout has appeared. We're going to start exploring what is the ctrout data object that we imported. So hint, this is data from Dr. Robert Lennox of Norse in Norway, which is really awesome that he's shared it for workshop purposes. So we're going to look into it. So head of ctrout will just print out the top few rows, the head of it, into your console. So I'm going to just expand that. So you can see we have an X, we have some date times, we have receiver number, we have the tag ID, species, lat long, and the length of what I'm assuming is the individual. So this is similar kind of data set that you might be familiar with in acoustic telemetry. And so we're going to start working on this moving forward. So another way you can explore it, you can click view. Has to be a capital V. It's this function is cap sensitive for sure. So if I run that, control enter, run that, it's going to open my ctrout in a tabular view that I'm familiar with so that I can display it. So from looking at this, I can see that X is really just the index. And I can see that the lat long are in like real funny units. And the date times are as expected. So you can also, again, we talked about this, we really want to see the structure of our object. So I'm going to do structure of ctrout. So let's see the output down here. So it's a data frame. It has a 1.5 million observations and it has 8 variables. So it has, 8 columns. And then it tells me what all the variables are. So X is an integer and these are the values of it. Date time, it's imported date time as a factor, which is basically as a character. And it has imported it as basically each date time is its own unique level. Same thing with receiver. It's grouped each receiver into its own level, tag ID into its own level, species into its own level. There's 2 levels, salmon and trout. And then lat, long, and length are all numeric. Okay, so numeric is the one with decimals and integer is the one without. I'm not sure if I got that backwards earlier. All right, so we're going to try some of our indexing that we learned earlier, but this time we have a 2-dimensional data frame, so you have to give it an X and a Y coordinate. All right, so first you do your X coordinate, which is your rows that you want to select, and I didn't put anything there. I want all the rows, all right? And then for columns, which is your Y coordinate, I picked 7. So you could do combine, and you can list all the columns that you want. This is just showing you that you can use the combine function within indexing. So I'm going to run that, and it's going to select all of column 7, and like all the rows of column 7. So the printout is screaming at me because there's 1.5 million entries, and it can't print them all out. So maybe let's do something a little bit nicer. So we're going to start using, instead of all these brackets that, as you can see, kind of get layered up really quickly, you end up like having brackets within brackets within brackets, and it gets quite confusing. We are going to start introducing some Tidyverse packages that make this a lot more human readable and a lot clearer to work with, in my opinion, especially for beginners. So we're gonna make sure that we have dplyr libraried. It should already be there because it came in with Tidyverse, but we just want to double check. All right, and so now we're going to basically do this exact same thing where we select column 7, but we're going to unwrap it from all those brackets. So dplyr has this really cool operator called a pipe, which is %, greater than %. And you read it, if you're reading it like a sentence, you read it as and then. So here, we're taking ctrout, the object, and then we're putting it into dplyr's select, and we're selecting column 7. All right, so this syntax of dplyr ... just basically, it's not required, but is basically just making sure that we are using the select function from within dplyr. So because select is such a common function name, I assume that base R also has a select function, and I just want to use the select function from dplyr. So I'm using dplyr ... select. So this is just a couple new operators, some syntax for you guys to learn, the dplyr ... syntax, and also the pipe. So pipes are annoying to type, as you can imagine. So it's Control-Shift-M is a shortcut, or Command-Shift-M, I guess, for Macs. So I'm going to run this, and this will be the unwrapped of the brackets dplyr way to do exactly what we just did. All right, so I printed it out, and this time it printed a little nicer. So it has just, row number, and then it has the value of column 7. However, it still can't print them all because there's 1.5 million rows. So to fix that, I'm going to basically select only a couple rows so that the printout will work. So this is how you would select a couple rows in base R. So again, put some brackets in there. So I'm selecting rows 1 to 5 in using base R code. And you can see that it prints it out as expected. However, dplyr, you can unwrap that and you can go ctrout and then slice rows 1 to 5. So select is for column selections, slice is for row selections. So if I just slice that, now I can see everything from in rows 1 to 5. You can also combine things for your using pipes. So I'm just going to type some code here, ctrout, and then I'm going to do Control-Shift-M, and I'm going to do a dplyr select. Oops. Select, and I want to select 7, and then, so Control-Shift-M, I want to slice 1 to 5. So I'm combining basically the two examples we just did. So take your ctrout data and then select column 7 and then slice just rows 1 to 5. And if I run that, I can see column 7, which is lat, and just rows 1 to 5. So pipes are a really great way to iteratively build your code, kind of like a sentence, like a human readable sentence. So step 1, select, and then slice, and then etc. So it's quite helpful. Now we've seen that our data set is really huge, 1.5 million rows. So I'm going to put that into, I actually don't know if this would work. I'm going to put that into ctrout full. I think I need to do an assignment operator here. Okay, no, equal sign does work. So I'm going to make a copy of it and call it ctrout full. So ctrout full equals ctrout. And then I'm going to take our actual ctrout and I'm going to just slice the first 100,000 rows. So now we have two copies. We have the full data set, we kept it somewhere else, and then the ctrout one that we're going to use moving forward is just a little bit smaller to make some of this code run a little bit faster. All right, so another example of unwrapping brackets. So to try to find the number of rows in the species column, so or like the number of unique species, has a lot of brackets in base R. So basically what you're doing is selecting the column species with this $ syntax, and then finding the unique ones, and then making it a data frame, and then counting the number of rows, right? So let's unwrap all of that using dplyr. So we're going to do sea trout, and then we're taking the distinct species, and then we're counting the number of rows, right? So distinct is the dplyr version of unique. But you can see this is much clearer to read and unwrap like that. So I'm going to run that. You can see there's the output says 2 for 2 species, which we already knew. There was salmon and trout. So similarly, this is trying to, this comment is no longer relevant. It's from test code. But you can see this is another base R way of filtering where species just equals trout, which the syntax is pretty crazy, lots of brackets and crazy stuff. However, filtering in dplyr is so much easier. So take sea trout and then filter where species is equal to trout. And that's it. And if I run that, it's printing out everything where species is trout. So obviously it can't print all my rows, but you can see that it's trout for all of them. Similarly, to get the mean value across a column in base R is this tapply function, where you take an index, or you take your data. So you want to take a mean of trout lawn. You want to have an index of what you group by, which is sea trout by tag ID, and you can find the mean. So we're trying to find the mean longitude per tag ID. We run that and it works, it gives stuff, but it's some extra syntax. So now we're going to use a bunch of dplyr functions. So we're going to take sea trout, and then we're grouping it by tag ID, and then we're summarizing it. And we're going to make a column called mean. And in the mean column is going to be the mean of the longitude. That's what that syntax is. All right, so when I run it, you can see that we end up getting tag ID and a mean out. So we named this column mean. We specified that in our summarize function, but quite nice to work with comparatively. All right, so we're going to move on to dealing with our date time. So when we looked at the structure of sea trout data, we saw that it was in a factor. Each date was its own kind of like text object. It wasn't recognized as numbers or dates. So in base R, you can use this as POSIX-CT function to do that, and it takes a little bit longer. It's slower to convert all those date times into dates. However, using a Tidyverse library lubridate, you can unwrap it. So sea trout and then mutate date time, the column, is going to equal, this function is year, month, day, underscore, hour, minute, second, or John likes to call it yammed hams. So we're going to use this yammed hams function against date time, rename it date time. And then now lubridate has made our column date time actual understandable dates, which is important moving forward. I also have some example code here. Lubridate's super awesome for dealing with time zones or when your data is in multiple date formats, etc. I'm not gonna show that though. All right, so we're gonna just do some example plotting. So first we're going to, in base R, just plot our lat long of sea trout. So it's taking a moment for me. It should show up in your plots window. Let it think for a moment. Aha, my plot showed up. All right, so my plot showed up and my library command went through. So now I'm gonna show basically how to do this in ggplot. So ggplot uses pipes as well, so sea trout, and then we're going to ggplot, and ggplot takes two basically inputs. So it takes the aesthetic, which is X and Y, etc. So the aesthetic is lawn lat, plus you have to add a plus, and then you add geom point. So you can add whatever type of geom, which is the geometry you want. So I wanted a point, just points for this one. So I'm going to run that, and hopefully it's a little bit quicker to display for me. I also think the screen share and running R is probably gets my computer going. So this is just basically the basic syntax of using ggplot. It's important to note that if this plus sign is not on the previous line, like if you put this plus sign down where geom_point is, R will not know to keep running. So you need the plus sign at the end of the line. So when R gets to the end of this line, it knows plus, oh, there's some more, and it looks down at the next line. Similarly, with the pipe has to be at the top so that when R is running, it sees pipe and knows that there's more, and then it goes and keeps reading the next line. Computers are pretty stupid. So you can see my plot showed up. It's just like a little bit prettier, but it's the same plot. So as I said, basically this is what ggplot takes. So this is a basic formula. So you have to specify your data, your mapping, which is your aesthetics, and your geoms. So we specified our data by passing ctrout pipe to ggplot. We specified our aesthetics, and then we added to the geom we wanted. So you can also build a plot and then just add geoms to it later. So we're building a plot where data is ctrout, mapping is x is lon, y is lat, and we're gonna put that in an object. And then we can add whatever geoms we want on top of it. So for this one, I'm adding a geom point again, but this time I'm gonna have an alpha of 0.1, which is kind of like a transparency option. I'm going to have the color equals blue, etc. So you can build kind of your basic, what you want your XY to be, and then you can test out a bunch of geoms really simply when you're exploring your data. So you can do, you know, throw different plot types, box plots, etc. at your basic plot that you've, object you've made. So this one will be almost exactly like the last plot I showed, except for we've changed the color and added the alpha value, which the alpha value is quite helpful when you have a lot of points that are overlapping each other. So you can see all the points instead of a big angry blob. I should also note that this intro to ggplot is actually the second, or the next page, the next lesson on our webpage. So this is making basic plots using ggplot. We've graduated to the next lesson. So yeah, there we go. My plot showed up. My dots are blue this time. You can't really tell the transparency because there's not really many overlapping points, but those are just to show you some of the options, basically examples. So now we're gonna get some more, I guess, useful data sets. So first we're going to take our ctrout data, and then we're going to group by month of date time, and we're gonna call that M. All right, so month is a lubridate function, I think, because we know which of the values in datetime is the month because we've specified in lubridate. So group by month, tag ID, and species. All right, so lots of groupings, and then we're going to summarize the mean of the longitude, and we're gonna call that mean. So I'm just gonna run that first part, and it should print out the data. Yep. So I get M, which is month, I get tag ID, I get species, and I get the mean for that combination of month, tag ID, and species. You can see this warning message. It's like a future warning. It says, this warning will become an error in the next major version of lubridate. So it's a future problem. So then I'm going to plot this. I'm going to make my aesthetic. I'm going to turn month into a factor instead of a number because I don't need to do math on it. I just want the months to be basically like text objects, month 1, 2, 3, 4, etc. I'm going to have the mean. So I'm going to have the mean longitude as my Y. I'm going to color the dots by species and fill the dots as well. And then I'm going to add a geom point. My points will be size 3, and my points will be jittered position. So it means they don't overlap each other. They kind of are a little off center. So I'm going to run just that section so you can see what that part does. All right, so you can see we got our salmon and our trout. We've got month as a factor, which is, you know, so it looks like we have April and May here for months 4 and 5, and then we have the mean longitude. So Maybe we want to flip that so that longitude runs the other direction. So you can do coordinate flip for that. And then we're going to make the colors a little bit more useful. We're going to have gray and gold as the colors because blue and red really don't represent the fish that we're looking at. So again, these are all just examples of how you kind of iteratively build your plot. So you add layers and calls and functions on top of your mapping that you've set. So now we have flipped the coordinates and we've colored it. Now we're going to, maybe we want to put a box plot on top of that so you can layer geomes. All right, so now I have my box plot on top and we're just gonna see what else we can do and add a violin plot on top. There we go. So you can see that in April, there are no salmon detected at all. So there's no mean longitude for salmon in April. So that's probably because they were only tagged in May, which is why there's no detections of salmon in April. And you can see our trout have a much smaller or more condensed longitude in April, and then they start moving away in May. So this is the kind of stuff you do just to explore your data. So there's other ways to present like this. We're going to use kernel density estimates. So I'm going to run this whole block, and the only difference here is this last line, the geome density. So for this one, geome density only works on the full data set. So I'm using sea trout full. That's something I just found when I was testing it. So I'm going to run that. This one's thinking because it's the full data set, so it's a little bit bigger. All right, here we go. So I'm going to zoom this one so you can see it a little bit better. So now we have some density contours around our mean longitude for months. This next one, we are going to do something similar, but we want to subset it by species. So that's this call to facet wrap. So we're faceting our plot by species. So we already have a species group, so it's really easy to just plot them by that group. And then we're going to make a pretty scale, and we're going to add some labels. So this is just, again, I'm just showing you some examples of different layers and different things you could use for your own plots. None of these are right or wrong. They're just, you know, any combination of them. We're also using a slightly different density plot call. So as Naomi told me yesterday, this is a really, really ugly plot, but I think it's cool. So this is basically, you have to interpret it as you want to. So this is kind of density estimates for their longitudinal distributions, but now it's grouped salmon and trout separately. You can also do this last one, which is per individual facets. So facet wrap by tag ID, and you're gonna get tons of facets for this one. As you can imagine, there's multiple tag IDs. In fact, so many that I'm pretty sure that when it prints it out, it's not gonna be super helpful, but just an example of things you can do and the syntax that you would use to do them. So even when I zoom in on this one, you can see like this one right here has a little bit of blue, a little bit of its density plot showing up. This is also our subsetted data set again. So it's doesn't have as much data as it could, but this is the syntax you would use if you wanted to find something. I also have my last thing here is just a little spiel about some of the changes. dplyr, R, and ggplot have all recently updated. So there's some links to show kind of the new documentation if you really want to look into what the changes are.
Thanks for watching the Ocean Tracking Network on YouTube. If you enjoyed this presentation, there's a good chance you'll like some of the other videos in this series. Click on the link in the description below for the workshop playlist, where you can learn more about the R programming language and some R packages suitable for exploring and plotting acoustic telemetry data. Keep up to date with our latest videos by tapping the subscribe button or clicking over on this list to see more workshops in this series.